Hello, and welcome to Agrosa Physics. Today is day 88, and what I like to do for this chapter is give an overview of the waves unit. Since this was very little problem solving, I'd like to talk about the different terms we discussed and their definitions. This will be a brief overview of all of the topics that we covered for the waves unit, and hopefully it will be a good review for the exam that's coming up. Now, first of all, we discussed different types of waves. We talked about transverse versus longitudinal. Transverse waves, the waves travel left and right, and the particles travel up and down. So the key is that the particle motion is perpendicular to the wave's motion. Longitudinal waves travel parallel to the wave's motion. So if the wave travels left to right, the particles will vibrate left and right. A wave transfers energy without transferring mass. So the particles vibrate and send their energy from one particle to the next, kind of like a domino effect. But unlike dominoes that are falling down when we're done, these particles are elastic and they return back to their original position. So you can constantly send waves, the energy in a wave, along the particles over and over again. So sound waves may vibrate, but they will only vibrate in a localized location. Each particle will vibrate the next one in turn, and that wave will be sent longitudinally. Longitudinal waves are also known as compression waves. We have compressions and expansions for longitudinal waves. We have crests versus troughs for transverse waves. We also had two different types of waves depending upon the material in which they traveled. Mechanical waves need a material in which to travel through. Sound is an example of a mechanical wave. Water is an example of a mechanical wave. We also have electromagnetic waves. Those can travel through space and all forms of light or electromagnetic. That includes visible light, ultraviolet light, infrared, X-rays, gamma radiation, microwaves, etc. After we talked about that, we discussed what happens when a wave hits a boundary. And every time a wave hits a boundary, three things occur. You have some of the wave is reflected, so it bounces back into the original medium. Some of the wave is refracted, which means it goes into the new material and possibly changes direction. But most importantly, it will change speed. The density differences affect how fast the waves will travel. Finally, some of the wave is absorbed, so the energy of the wave is dissipated slightly, and that ensures that a wave can't reflect infinitely. So ultimately, a wave will diminish every time it hits a boundary and eventually dissipate. Now we discussed the characteristics of the waves, such as frequency, which is the number of cycles a wave vibrates per second. A C note, for example, is 256 hertz. So the unit for frequency is hertz, and that represents 1 over second. So a C note will vibrate 256 times every second, as opposed to visible light, which could be in the 10 to the 14 hertz. So each form of a wave will have different frequencies depending upon the type of wave that it is. We also discussed wavelength, and that had to do with two particles on a wave that were in phase. If you remember, in phase was when waves did the same thing at the same time, so either the wave was vibrating with a subsequent wave near it, or two particles on a single wave may be doing the same thing at the same time. We discussed the fact that swinging on a swing set is an example of in phase or out of phase. When the swingers are swinging together, that would be in phase. If they're opposite one another, they would be out of phase. And you could have various degrees of being in phase or out of phase. In phase we called 0 degrees, and out of phase was 180 degrees. Typically, in phase would be two crests near each other, and out of phase would be a crest versus a trough. After we talked about that, we discussed amplitude, which was the strength of the wave. Basically, it represented how far from rest a particle vibrated on a wave. The farther it vibrates, the stronger the wave, the more energy the wave has. Amplitude has a direct square relationship with the energy. So if you double the amplitude, you quadruple the energy. If you triple the amplitude, you increase the energy by 9 times bigger. After we discussed that, we had an equation that represented the difference between the wavelength, the frequency, and the velocity. Now, wavelength was how far the wave travels forward as one particle makes one complete wave motion. Typically, you'd think about that in terms of one complete sine or cosine graph from math class. Now, when we have the wavelength and we have the velocity and the frequency, the equation becomes v equals f lambda. If we have the time period, which is reciprocal of the frequency, so t, capital T, is 1 over f, the equation would be v equals lambda over big T. So we have different equations for determining the speed of a wave. In addition to that, we then discussed the Doppler effect. The Doppler effect was the apparent change in frequency of a wave depending upon the relative motion of the objects involved. If the object that is observing the sound and the source are moving closer to each other, the apparent frequency goes up. If the apparent frequency goes down, if the particle, if the observer and the source spread apart or move farther apart from one another. If you travel fast enough, you can reach what is known as the sound barrier. And the sound barrier is a level of energy that is where all the crests line up as an object tries to travel faster than the sound wave that it's produced. If you can exceed the sound barrier, you can actually break the sound barrier and you produce a shock wave behind you. When you're riding in a boat, the wake of a boat is an example of a shock wave. If you have enough energy and you break it quickly enough, you can produce a sonic boom. So when you hear the crack of a whip, that is breaking the sound barrier, and the sound of the whip cracking is an example of a miniature sonic boom. All the energy is released in a short period of time and can cause quite a bit of damage to surrounding areas. If a whip hits a person, it will break skin. If sound waves have a sonic boom, it could break glass, it could shatter windows, etc. So sonic booms can be produced localized with a whip, or in a general way if, let's say, a jet plane breaks the sound barrier near houses or cars. After we talked about that, we discussed interference. We have two types of interference. We have constructive and destructive. When we have constructive interference, it causes the particles to combine and form a bigger wave. So we do A plus B. If two crests come together, the middle point where they meet would be A plus B, and they would continue on in their same direction. Waves don't bounce back off each other like particles. They travel through one another, kind of like how ghosts would travel, if we can imagine ghosts traveling through another object, often depicted on movies and television shows. We have destructive interference as well, which is an example of a crest and a trough coming together. And if that's the case, you subtract the two. If the crest and the trough are the same size, you would actually have zero displacement for the resultant. When we have interference and we add the waves together, we have a fancy term for the resultant. We call it the superposition of the waves. So we just add the different forces acting on the point. We could have multiple waves. We could have 2, 3, even 4 waves. And we add them together to form the resultant displacement, which we call the superposition. When we have waves traveling either through each other that have the same frequency or bouncing off one another and traveling back onto itself, kind of like when we send a string on a guitar or possibly a wind instrument, or even if we're using a spring to represent a wave pattern, we can produce what's called a standing wave. Parts on a standing wave that stand still are called nodal. Parts of a standing wave that move in their maximum displacement are known as antinodes. So we have nodes and antinodes. The wave is truly traveling left and right still. It's just that the particles appear to only be moving, if it's a transverse wave, vertically, and if it's a longitudinal wave, horizontally, instead of the wave appearing to travel. Like the Doppler effect, it's an apparent standing wave, not an actual standing wave. We discussed the difference between string and wind instruments. String instruments are based on the velocity of the wave because of tension, and wind instruments are based on the speed of the wave because of the temperature of the sound, temperature of the air around. So the sound waves travel at different speeds depending upon the temperature. The basic equation is 331 plus 0.6 T, and the T is measured in temperature, in degrees Celsius, of course. If you have 0 degrees Celsius, you're at the air temperature of 0 Celsius, the waves travel at 331. In room temperature, which is 20 degrees Celsius, it would be 331 plus 12, or 343 meters per second. So typically the two speeds of sound waves are based on 0 or room temperature. But it could be any value between 0 and any value that you're given. After that, we discussed the speed of the wave on a string in terms of its equation, which is V equals radical force tension over mass per unit length. The mass per unit length is based on the string, or the mass density and the length of the string. So we leave those terms together, although we could simplify the equation mathematically. We don't. After that, we discuss resonance. Resonance is when an object vibrates at what we call its natural frequency. If we have two objects that vibrate at the same frequency, we can have what's called sympathetic vibrations. So one wave source can cause another object to vibrate at its natural frequency because it will sympathetically vibrate at that frequency. You can use that to tune guitar strings with a tuning fork or with another string on the instrument. And it can cause, a common example is the fact that water vibrates in a microwave because the natural frequency of water has the same value as the frequency of microwaves themselves. After we discuss that, we discuss the beats of a wave. And that's when two wave patterns are close together but not exactly in tune, and you hear a number of beats per second based on the difference between the two frequencies. 256 and 260 would produce 4 beats per second. We could actually find the resulting frequency by averaging together. When we produce a beat pattern, we hear what's called a warble, and that's alternating loud and soft sound, kind of like this, wah, 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 which is undesirable if you're trying to tune an instrument, and you would actually try to produce a situation where you only hear one note and no warble itself. Now that concludes all the topics that we covered. We did a number of sample problems throughout the unit. We did some worksheets dealing with the terminology. Remember that although this is strictly a conceptual, the majority of the concepts are conceptual, there are some calculations that can be done, and we do have a number of equations that we dealt with. The Doppler equation is not on the Regents exam itself. It's mostly a supplemental equation. However, it's a ratio between the speed of sound or light or whatever the wave produced is and the difference between the observer and the source of the wave. By using that ratio, we can calculate the apparent frequency of the resulting wave due to the Doppler effect. Now that concludes our overview of the waves section. This should be good for review for the waves test, but make sure you study as well on your own so that you can get that perfect score. Thank you.